Welcome everybody to the lecture number 11 in electromagnetic fields. Today we're going to talk about the steady state current. So far we had studied like static charge and their production of electric field. Today we're going to study the effect on free charges when there is like a steady state field or under like DC current. What would be the situation and what can we like analyze and learn regarding this case. So we're going to start by the current density. So if we consider like a medium with n charges per unit volume, each charge does have a q column, and those charges moves with velocity u. So the amount of charge passing through any surface, delta S, an, where an is the normal out of the surface, in time delta t, this amount of charge that pass through this surface in delta t time equal the number of charge multiplied by the q of charge. So this is the number of charges per unit volume. So this is raw volume multiplied by the velocity dot delta S dot delta T. This will be the total charge passing through the surface in this time. If we calculated delta T by delta Q by delta T, which is the current I, we'll get this relation here in Q U multiplied by or like dot product with delta S, and the first one in QU is J, which is the volumetric current density. So starting from this definition of current, we can calculate the total current through like a larger surface, which is the integration of J dot ds. So this is the case. So the total current flowing out of any arbitrary surface is J dot ds. If we have multiple charges, like we have like multiple charge carrier, each one with like its own velocity and its own charge and its own charge density, similar to the case of semiconductors, for example. So the volumetric charge density is the sum of the volumetric charge density of each of those kinds. In conduction, the conduction current is a result of a drift motion of charge carrier under the influence of applied electric field. So if we have free carriers or like charge carriers and we apply an electric field on those charges, those charges will be drift or moved with a certain velocity. The constant of proportionality here is called the mobility. So we can say that for conductors, the carriers are electrons, so the velocity is in the opposite direction of the electric field, and the constant of proportionality is the mobility, and this mobility is higher for better conductors. So we now know the velocity of charge, free charge, is proportional to the applied electric field by a constant, which is the mobility. For conductors, we know that we just said the volumetric current density equal volumetric charge density multiplied by U, or we can just replace U with minus mu E, and we know that rho E, the volumetric charge density, is the number of charges per unit volume multiplied by the charge of an electron. So this quantity here is called, because rho E here is negative, is called conductivity, and we have the charge density, the current, volumetric current density is proportional to the electric field with the conductivity constant. For semiconductor, we would have like two kinds of charges, which are the holes and the electrons. So the conductivity would be like sort of like the sum, what is the volumetric charge density for electron multiplied by its mobility, plus the volumetric charge density of holes multiplied by its mobility. And this is a table of the conductivity for different materials, just for your information. So now let us see something very similar, or like it is the Kirchhoff's current law from the electromagnetic field perspective. So in physics, we have the conservation of charges, the total amount of charge in any, like that charge is preserved. So we have a conservation of charge. So if we have certain closed surface, the total charge out of this surface, like this closed surface, as a function of time is the current. So if the total charge in a volume changes, it means that some charges goes out and they will create some current. We just said that the current I equal the integration of J dot ds if we choose the arbitrary surface to be a closed surface. This means the total current going out of this surface is this quantity here. We know that current equal dq by dt. We have the negative sign here because this is the total charge inside the volume and this is the current going out. So when this charges decrease, it means that the current goes out. If the charges increase, it means the current goes in. So this sign is related to the direction of the current, the definition of the positive and negative. Positive here is out of this closed surface. And Q can be like expressed as rho d volume over the volume surrounded by this closed surface. And here, J dot ds, we can use the divergence theorem to write it as the divergence of J d volume. We know that J equal, so from here when we do this, we have this right hand side and this is the left hand side. We know that the divergence of, we can just conclude that the divergence of J equal minus d rho by dt, and this is called the equation of continuity. So we start by the current out of the surface, the definition, and we invoked the divergence theorem. From the divergence theorem, we can equate these two quantity, divergence of J and the derivative with respect to time of the volumetric charge density with a negative sign, and this is the equation of continuity, which is some sort of the law of conservation of charge. So at steady state current, nothing is changing. Steady state current means everything is constant with respect to time, so the right hand side will equal 0. And in this case, the divergence of J, which equal from the divergence theorem, which equal with some constant J dot ds, both of them equal 0 in this case, because here this is 0, so divergence of J will equal 0. The J dot ds, total current change out of a closed surface, will equal 0. And this can be like written and generalized as Kirchhoff's current law. Total current at any node equals 0. So if we have any node in a circuit, we can put like a sphere around this node, and we apply the conservation of charge or the equation of continuity. And under this condition, the total current out of this surface, which is the surface of a sphere, equals 0. So the total current out of this point also equals 0 if we have the sphere like shrinking to the limit of just a point. So this is a usage of the electrostatic field equations and system to prove current Kirchhoff's law under steady current, no variation with time, which is a steady state. So when the steady state current crosses a boundary between two media, the two media does have a different conductivity, there will be some boundary condition. Those boundary conditions are coming from those two equations. The first equation is that the continuity equation, divergence of J equals 0, and the other one is the curl of E. So here, because we have free charges, E equal J over sigma, so curl of J over sigma equals 0. So we have those two. This is the conservation of electric potential, but written with E equal J over sigma, and this is the continuity equation. These two are the differential form, and those are the integral form. So those are the boundary condition for current flowing under steady state conditions. From these two laws, we can conclude these two boundary conditions. E tangential, J over sigma equal E. E tangential 1 equal E tangential 2. And here, the J1 normal equal J2 normal. This is the volumetric current density in the normal component is continuous. So those are the boundary conditions for the case of steady state current flowing between two different medias with sigma 1 and sigma 2. So let us have this example to apply what we learned. We have two conducting media. Conducting media means they are carrying, or they just have free charges. So two conducting media with sigma 1 and sigma 2, they are separated by an interface as shown in figures. The steady state current in medium 1 at point B equal J1. It makes an angle alpha 1 with the normal. Determine the magnitude of the current density at point B in medium 2 and its direction. So J1 is given, alpha 1 is given, sigma 1 is given, sigma 2 is given. We want to have the value for J2 and the value for alpha 2. So this is very traditional and common boundary condition problem. We have two boundary conditions, which is J normal in this case. So let me copy this. So we have two boundary conditions. Number one, J normal is continuous. So J normal is J1 cosine alpha 1 equal J2 cosine alpha 2. So J1 and alpha 1 are known, J2 and alpha 2 are unknowns. E tangential 1, which is J1 over sigma 1 multiplied by sine alpha 1. When we just write two of them and we multiply like the cross multiplication, we get this equation. As we did many times before, we can just divide like this equation by this equation. So it will be sigma 2 tan alpha 1 equal sigma 1 tan alpha 2. So sigma 2 tan alpha 1 equal sigma 1 tan alpha 2. Now we have the value alpha 1 is known, sigma 1 is known, sigma 2 is known, so we can find the value for alpha 2. Once we know the value for alpha 2, we can substitute in any of those two equations. There will be only one unknown, which is J2, and we can get J2. Another example, an EMF is applied across a parallel plate capacitor, so certain potential here. The cross section is S. The space between the two conductors is like filled with two media 1 and media 2. Media 1 is D1 sigma 1 epsilon 1. Media 2 is D2 sigma 2 and epsilon 2. And it is required to determine three things: the current density between the plates, so current density in medium 1 and in medium 2, the electric field intensity in both material, and the surface charge density on each of the plates. So let us see how can we solve this problem. So we know that the potential equal I multiplied by R1 plus R2, because those two plates or those two media here are in series. We know the current, the field, everything is normal to this structure, and because we have we ignore the fringe effect on the side, and we have like symmetry or infinity along the normal direction. So we know that the potential equal I multiplied by R1 plus R2. R1, we know that it's length divided by conductivity and cross section. We know that J equal I over S. So if we take I over S from here, what is left would be V divided by this bracket without the S, which is D1 over sigma 1 plus D2 over sigma 2. We just can do the math. And now we have the first requirement, which is the current density. One very important thing here, when you have a problem with symbols, the solution must be in terms of the given. So here what is given? What is given? Epsilon 1, epsilon 2, sigma 1, sigma 2, D1, D2, and potential. So you must bring the solution in those given parameters. So here sigma 1, sigma 2 are given, D1, D2 are given, the potential, the EMF is given. So those as if we have numbers. So now we define the current density in terms of the given variables. Number one, we need to find the electric field intensity in each media. We know that the potential difference equal E dot dl, and here it's equal E1 multiplied by D1 plus E2 multiplied by D2. We solved this problem before, where we know that the electric field is uniform in both media. So we can find the relationship between those. So we have this is unknown, this is unknown. D1, D2, and phi are knowns. From the boundary condition of continuity of normal component of the current density, we know current density 1 is sigma 1 E1, current density 2 sigma 2 E2. So we have those equations, we have those two equations. So we can solve, just substitute E2 with the value of sigma 1 E1 divided by sigma 2, and we now can find the value for E1. You need to check the right hand side, because here this is not a solution because E2 is not known, but this is an answer because all the parameters are given. So now we find the value for E1. We can just, from this equation, we get the value or the expression for E2. The third requirement is to find the charge density on the upper and lower plates. We know that the surface charge density equal D. For on the surface of a conductor, it's equal D, which equal epsilon 1 E1. So here, this is positive, so the field is going out of this plate. So the charge on the top side is positive and equal epsilon 1 E1. E1 is given, so we can find rho S1. On the bottom side, the field is going in the conductor, so it has a negative charge, which equal epsilon 2 multiplied by E2 with a negative sign. E2 is known, so now surface charge density is found. So one important thing here, that at the interface between the two dielectric, we have E1, we have E2. Because of this setup, we'll find that there will be some charge at the interface between the two dielectric, which equal E1 minus, so E2 minus E1. So E2 minus E1 will give us the rho surface at the interface between the two conductors. We can see here that those two quantities are not equal. If we consider this charge as well, we will notice that the charge S1 and S2 on upper surface and bottom surface are not opposite, so their sum is not equal 0, but the sum of all the charges equal 0. So this setup would induce some would accumulate some charge density at the interface between the two dielectric. So when we talked about the electric field behavior inside conductor, we stated that inside the conductor there is no free charge, there is no electric field. Rho equals 0, epsilon E equals 0, and rho equals 0. And we said that if we introduced charge to a conductor, all what's going to happen is this charge will be distributed on the surface to achieve equipotential volume and surface for this conductor. So now we are in a position that we can learn and study what will happen if we just introduced, some charge on a conductor. So let's start from this continuity equation. So from the continuity equations, divergence of J, the current density, equal minus d rho by dt. So if we just bring them, we express J as sigma E, so now we have sigma divergence of E equal minus partial rho partial T. So we write it this way, and we can divide both sides by epsilon. So we have divergence of E. We know that divergence of E equal rho over epsilon. So divergence of E equal rho over epsilon plus partial rho partial T equals 0. The solution for this equation does have this format here, and rho naught is the original charge density or the boundary condition at time equals 0. So if we have a conductor and at certain time we just throw some charge density on this conductor, what's going to happen? The conductor or the volumetric charge density will take this format. If we looked here, we'll find that this quantity here is very, very large. So this is like minus 10 to the plus 19 times. So for any very small quantity of pico or femtosecond, this quantity here will be e to the minus 1000, which is almost 0. And this time is called the relaxation time. So this equation here equal T over tau. The relaxation time here is really very, very small, which means instantaneously, or like in 10 to the minus 19 or 10 to the minus 18 second, rho will equal 0. And this is the time it takes the charge to move on the surface of the conductor to adjust, or like the boundary condition of constant equipotential surface and volume for the conductor. Also, through like the equations that we learned so far, we can talk about the power dissipation. When we apply electric field to charge carrier, when we have like some free charges in a media and we apply electric field, they move with velocity u, and this work done by the electric field on the carrier can be calculated. It's force dot dl. Qf is the force dot dl. If we have like a small volume, the total work done would equal n, the charge per unit volume, Q E dot dl. So this is the work done. So the power, which is the derivative of work with respect to time, will equal this equation, which is dl by dt will equal u, the velocity. So we have nqe dot u dv. We know that nqu equal j, so the power per unit volume equal j dot e. So the total power equal j dot e integrated over the whole volume. Now we're going to express dv as two components, dl and ds, a base and length. And we can just redistribute those items or those terms, e dot dl in one integration with respect to dl, j dot ds in double integral with respect to ds. And we know that this is I, and we know this is V, and from the electrostatic field equations we can prove that the power dissipation equal V I, which is the regular law of power dissipation. One final thing also that we can use the electrostatic for is the equations for calculating the resistance in a certain situation. So if we have like those two conductors and we apply some potential between them, and if we need to calculate resistance, there is a nice way to do that. This is through the sort of like similarity between capacitance and resistance. So for capacitance, equal Q over V. Q, the free surface charge, is d dot ds, or epsilon E dot ds. The potential is E dot dl. So the resistance is V over I, which is minus E dot dl. I is J dot ds. So this is the same. And you can see that here the charge equal epsilon E dot ds. The current equal sigma E dot ds. So there is a similarity between R and 1 over C. So we can say that R multiplied by C equal C divided by G, which equal epsilon over sigma. So if we know the capacitance of this setup, we can calculate also the resistance of this setup through this similarity between C and G, or like C and 1 over R is proportional to epsilon and sigma. So if we know the capacitance for any setup, we can find its resistance. This also is one of the things that can be done for one of the usages for the electrostatic field in solving steady state or circuit problem as well. We have a homework number 5 due in a week. This is the last homework before the final, and those are the learning objective, and we'll be waiting you in the discussion session. Thanks everybody for watching, and see you shortly. Goodbye.